Hi, I'm Coach Cowland, and in this presentation we're going to look at waves. So a wave is a disturbance or oscillation through space and time that transfers energy from one point to another. One of the important things to consider is that it's energy that's moving, but not the actual matter itself. Waves are closely related to simple harmonic motion and circles, and some of the variables and equations from the other two sections are also prominent in this unit as well. So when we look at the parts of a wave, we can see that there are crests that are divided by troughs. Crest, trough, crest, trough. The wavelength. Um, the definition of the wavelength is the length from any point on one wave to the corresponding point on the next wave. So, for example, it could be from crest to crest, it could be from trough to trough, or it could be from any point here to the point on the next wave. The symbol for wavelength is what looks like an upside down Y. It's actually lambda, and the unit of wavelength is the meter. The amplitude of a wave is the greatest distance from its rest position. So it's the measure from this horizontal point here, which is considered a rest position, to either the crest or to the trough. And in mechanical waves, the amplitude is a reflection of the energy of that wave. The greater the amplitude, the greater the energy the wave has. And a good way of thinking about it is to think about water waves. Ripples have very little energy, but tidal waves have huge amounts of energy. The reason why we talk about this only in mechanical waves is that in electromagnetic waves, the measure of energy is a little different. The frequency of a wave is the number of complete waves that pass a point in 1 second. The frequency is inversely proportional to the period of a wave, which we'll talk about later. So in order to find out the frequency of a wave, what I would need to do is to count how many waves pass a point and divide that by the amount of time that it took. Um, we use frequency when we talk about things like radio waves. If we talk about the frequency of a radio station being 50 megahertz, that means that the frequency of the radio station was 50 million hertz. I should say that the frequency of a wave it has units of hertz. The period of a wave, as I said, is inversely proportional to the frequency, and it is time it takes a complete wave to pass a single point. If the frequency is very high, this means that the period will be very small. The unit of the period of a wave is seconds. The velocity of a wave v is equal to f lambda. Frequency times wavelength equals velocity. Now, this is the velocity not of uh, 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 the matter of the wave, but actually of a part of the wave. For example, the crest of the wave. So, the velocity of the wave is how fast the crest is moving through the matter. There are two types of waves, transverse waves and longitudinal waves. The first one we're looking at now is a transverse wave, and we can see that the wave is moving from left to right, but we can see that the amplitude is going up and down. Note that the red dots here are the material in which the wave is passing through, and they aren't moving from left to right, they're actually just moving up and down. The other kind of wave is a longitudinal wave. And in a longitudinal wave, you can see these areas of high density and low density. The areas of high density are in fact the crests of the wave. And in between each area of high density, this area of low density is the equivalent trough. When people think of waves, they usually think of transverse waves rather than longitudinal waves. However, longitudinal waves are the kinds of waves that we experience the most, as these are the kind of waves that we experience when we hear sounds. Sounds are longitudinal waves. Interference. When wave crests meet each other, interference happens. It can be either constructive or destructive. If both amplitudes are positive, or both negative, then they add together to make a larger amplitude, giving you constructive interference. Here's an example of constructive interference. So both wave crests travel together, they meet, and the amplitude for the instant that they are together is the sum of the amplitudes of each individual wave. The opposite of constructive interference is destructive interference, where the amplitudes are opposite to each other. When they come together, they cancel each other out, and then they carry on going their own separate ways. So this is what destructive interference looks like, or negative interference. You can see that they cancel and then they keep on going. Come together, cancel, keep on going. Okay, thanks for watching.